And hello, welcome again YouTube. Welcome to this video of Labview frequency analysis. So today I want to continue where I left off the last time. Okay, last time we were talking about why Fourier transforms are not enough in analyzing transient response of systems. So Fourier transforms are good for steady state behavior, so semi-steady state, where let's say you have a microphone volume giving a particular frequency at a fixed amplitude. But once your amplitude starts changing, for example, if there is a microphone feedback, and it's very unpleasant sound, then you have exponentially increasing volume over time. The other way you can think about it is where you have this damping effect, where, for example, again, you have your spring mass dashpot system. And what it does is that over time, the frequencies will actually damp. They will get smaller and smaller. Again, Fourier transforms do not capture this very well because there is this time varying part of this oscillation. So since you cannot do Fourier transform, Fourier transforms are not sufficient to describe the behavior, you will need the Laplace transform. Okay, what is the Laplace transform? Okay, Laplace transform, if you take a look at the definition, it is the Laplace transform of s of some function ft, or we can call it fs, is the integral of ft times e to the minus st dt. Okay. But how does this relate to the frequencies, and where do all the frequencies and the exponential parts come in? It's very hard to see just from this s. Okay, s looks a bit. You can just do the integration, but you don't really know what s means. So this is just something to give you that intuition. Okay, so Fourier transforms, they are using exponential 2 pi I kt blah blah blah. Okay, that's definitely valid, and they are there to extract the frequencies. But how does this e minus st extract both the frequency part? How does it extract both the frequency part and of course the magnitude part? Let's say this is a damping oscillation, right? So you have e minus at, okay, sine omega t or sine kt, whatever that coefficient is. All right, how do you extract that? So, okay, I assume you have maybe some experience with Laplace transforms, but if you don't worry. I will quickly go through. All right, so basically there are usually tables of worked out Laplace transforms. You can just find them online. This is one of the examples here. So some of the common Laplace transforms, okay, Laplace transform tables. Okay, you see them, plenty of them online. Okay, you just Google and everything will be there. Okay, so some common Laplace transforms. Okay, all right. So let me get them written in LaTeX. Okay, so the question is, so what do Laplace transforms do, and how do we extract the frequency from them? All right, so how do we extract a frequency from a Laplace transform? Okay, so right, one of the things, besides looking at this, we look at definitions first, then I'll use the table to help you see where the frequencies are. Okay, so let's say you go to this, you search Laplace transforms and you go to Wikipedia, right? Wikipedia will tell you, all right, we have this s equals to some j plus sigma plus omega t. Right. Okay, where is this complex? Yeah, s is actually some complex number. All right. Okay, so yeah, on Wikipedia you will see this. You'll see this thing S equals to sigma plus I omega. Some people use J omega for the what do you call that? For the complex number, right? So let's just write that down first. We note that for Laplace transforms, and so we will note some Laplace transform and the intuition, right? So S equals to sigma plus, I'll use I omega. Okay, so this is what it'll look like, sigma plus I omega. Alright, so how does this actually go in? Remember, we actually have an e to the minus st here, right? For Laplace transforms, we have, okay, e to the minus st. Alright, whereas for Fourier transforms, we have e to the 2 pi ikt. Now, what's so special about e to the power of some imaginary number, right? So recall, when we have e to the power of some imaginary number, e to the power of, for example, I theta, this will be equals to sine theta plus cosine theta plus I sine theta. Okay, so I'll just give a space there. Let's see whether it turns out right. Yes, this is e to the I theta. This is also known as Euler's identity. So if we substitute this in, we substitute the sigma and I omega in. So let me quickly just write that down into the e to the power minus st, and we expand them out. Alright, what do we get? Okay, what do we get here? So we can get, let me draw this. Okay, e to the minus st equals, e to the minus st, it will be equals to, so we just substitute the whole thing in there, and this is what we will get. Alright, let me delete first. Alright, this is what we looked at. Okay, so we get rid of the s, and then you will see this. Oopsie. One more. There we go. Okay, so you see there's an e to the minus sigma t and e to the minus I omega t. Right? Okay, so e to the minus sigma t, then e to the minus I omega t. Right? Okay, hold on. That's better. Okay, I isolated out the brackets and everything, so this is what we will see. Okay, you have a e to the minus sigma t and e to the minus I omega t. So what is this part actually? Alright, I should not put a plus there. This should be a times. Okay, much better. So you see, over here we will actually have one part of the transform leading to some exponentials, this sigma t part. Then the I omega t actually becomes sines and cosines, because recall e to the minus e to the I omega I theta equals to cosine theta plus I sine theta. The cosines and sines will actually appear here, and the exponential part where you have all the damping, damping and exponential increase, for example in volume, this will appear here. Okay, so this will appear here inside this first part. This first part will have this exponential part, whether it's decay or increase. Alright, so that's basically, in a sense, you have this Fourier transform, and then you just multiply it by some I guess you can think of it like you multiply it by some what do you call that? Yeah, exponential term, right? So this is an imaginary exponential number, which actually is a sine and cosine. Okay, then you can multiply it by some real exponential number. So e to the power of sigma t, for example, and voila, you have somewhat of a Laplace transform. Okay, so you have somewhat of a Laplace transform. So that's how you get your Laplace transform from your Fourier transform, so to speak. So it's a hand wavy way, but it's an easy way to think about the transforms and how they relate to each other. Okay, so how then do we get the various frequencies? Okay, so to get that, you will need to know some of the Fourier and Laplace transform identities. Okay, so I'm going to write some of it down into LaTeX, and I'm going to speed this part up. Okay, so let's take a look at some common Laplace transformations. Okay, section common Laplace transforms. So I assume you would have known some Laplace transforms before, but if not, okay, basically Laplace transforms are the result of doing this messy integral here. You do your factorization of whatever, you do your integration, you apply your limits, then you kind of simplify and everything together. The end result will be something like this. Remember, this is the messy integral, right? E to the minus st dt. Okay, so let me put the definition here so that it's easier for you to see what's actually going on. Okay. Right, let's see. Yep. Remember, Laplace of some function ft is equals to this. Okay, all of these here are the end results. But don't worry about the math. I want you to notice some patterns here. Okay, so Laplace of cosine omega t is s over s squared plus omega squared. Laplace of sine omega t is omega over s squared plus omega squared. Laplace of e to the at is 1 over s minus a. Laplace of e to the minus at is 1 over s plus a. So what do you notice? Now ignore whatever you see in the numerator. The important part here I want you to focus on is the denominator. So, okay, looking at the denominator. Alright, so what do you notice? What do you notice about the denominator? Okay, let's say if for sines and cosines, alright, we will have this, okay, s squared equals to minus omega squared. Right? S squared equals to minus omega squared. This is if you equate the denominator to 0. Okay, equate to 0. Okay, equate it to 0. Right, what will you get? S squared equals to minus omega squared. And what do you have? If you solve this equation, S becomes, alright, I omega. Okay, S equals I omega. So, look at it. This is interesting. Where does this I actually pop up? If you have e to the power of minus s, or e to the power of s in this case, e to the power of minus I omega, or e to the power of minus I omega t, for example, you will get back your sines and cosines, right? When you have e to the I omega t, or e to the I omega whatever in this sense, you'll get sines and cosines. Note, okay, e to the power of I omega equals to cosine omega plus I sine omega. Alright, I didn't put the t in here, but this is just something very interesting for you to note. You see, all your frequencies actually appear inside your denominator. Now likewise for the exponential terms, okay, damping or unstable system. Okay, the unstable system I'm referring to is if you have very much exponential increase, you do the same thing. Okay, s equals to minus a. All right, s equals to minus a. If you take a look at e to the minus at, s equals to minus a, so the power is at the bottom, or is s equals to plus a for e to the minus at, or again s equals plus a for e to the at. So let me quickly put that down. So s equals to minus a for e to the at. Let me change a bit. So I'm going to switch this down here. For e to the minus at, s equals to minus a. And for e to the at, s equals to plus a. So notice something very special about the notice a pattern here. Wherever you find s becoming a real number, the real part of s, you will actually get all these the exponential part of the Laplace transform. Wherever you have this imaginary part, you will get the oscillating part of the Laplace transform. Okay, so let's say a general expression, right? You can sort of guess a pattern here. If s equals to s equals to sigma, or for example a, I will not use sigma since we are using a here. If s equals to a plus I omega, then what can you expect the solution to be? Okay, my time's up. I don't want to take too long, but you can expect this solution to be something of this sort, right? Okay, sine omega t. Sine omega t. What can you expect this to be? All right, you can expect it to be in this form. All right, so okay, you can either have a partial fraction or something. So fraction a over s square plus omega square plus fraction b over s plus a, right? You can sort of guess a Laplace transform for this kind of equation, and you will actually be right. If we look at the table, if we look at a Laplace transform table, okay, so you can see something very interesting here. Okay, if we look at EAT, e to the power of, for example, AT sine BT, right? You will see that it will look like this. Okay, let me type it out for you. This is from the website. I'm going to speed up the typing, of course. Okay, so if you have this, so we looking at the patterns here, we could guess the Laplace transform. And if you look at the actual Laplace transform table, we will have something of this form. Okay, something of this form. All right. Of course, if we replace it by s plus a, for example. If you replace it by s plus a, you would have something of this form. All right. So this is a more stable system because this one, remember, this is e to the power at. A is positive. A is positive and a real number. So this will actually, shoot past, go to infinity as time goes to infinity. This one will go to 0 as time goes to infinity. But what do you notice? You can actually look at the denominator. Somewhat, if you actually do some sort of partial fractions there, you can actually see a sort of a pattern occurring, right? So let's say you get the bottom to be equal to 0, right? Maybe, okay, this is sort of the intuition we get. No, we didn't quite get the Okay, I didn't quite get the right answer, so to speak, but if you actually equate the bottom to 0, it'll be quite interesting to look at. Equate the bottom to 0, for example, for this one, right? So let's say, okay, s plus a squared, so that's s plus a squared equals to omega squared, okay, or minus omega squared. So this is what happens. All right, so what happens if you take the square root of both sides? Okay, so you have plus minus, right? Plus minus s squared plus a squared equals to plus minus omega, I omega. Right, so this is what it will look like. Plus minus s plus a equals plus minus I omega. Now the plus minus is kind of redundant here. I will just put s plus a equals to some I omega, right? So what happens? Okay, so s will be equals to I omega minus a. Okay, this is very interesting, right? I omega minus a. So where's your frequency part? Your frequency part will be the imaginary part, and your exponential part will be this a part. So where, if you do a Laplace transform, you can basically see, just ignoring the numerator, you can actually see where the relevant exponentials and frequencies actually come from. You can just look at the denominator of the Laplace transform, equate it to 0, and then you will get all the relevant frequencies. So imagine if you have a superposition of many frequencies. Just look at the denominator and you'll be able to find all the relevant frequencies there. Okay, so let's see how much time I have remaining. I'm at about 22 minutes. So let me just draw one more graph to kind of finalize it, right? So you want to compare Fourier transform graph. Let's say here, you actually compare, some amplitude versus a frequency, right? Okay, so you have lots of plots here of a varying amplitude, just like you saw. However, for Laplace transform, how do you actually visualize this? Okay, you won't be actually able to see it so clearly. Okay, because s is a complex number, right? S is a complex number and is equals to sigma plus I omega. Remember, this is the frequency, this is the part pertaining to the exponentials. So you'll have a real plane and an imaginary plane. So if you were to plot the frequencies over here, you will be able to see the various frequencies over here. Also, if this is 0, if you plot the parts where there are some numbers where s, the real part of s is actually positive. The real part of s is positive. Alright, what happens here? If the real part of s is actually positive, then you'll have e to the at, right? E to the at. So this is increasing. If the real part of s is like negative, then you will have e to the minus at. So this is sort of some intuition you will get, right? Some intuition you will get. Alright, so if you want to see the real and imaginary planes, you will be able to see both the exponential components and of course the various frequencies. However, in this plot you won't be able to see the magnitude as well, so you'll probably need some other kind of plot to actually deal with that. But hopefully that this gives you an intuition into how to think about Laplace transforms and where do you actually get all the relevant frequencies and exponentials from. And you can actually look at it just by looking at the denominator of your Laplace transform. Okay, so that's all I have for you. Hopefully this clears up any potential confusion between Fourier and Laplace transforms, how they relate to each other, and how to actually extract the information. okay, the relevant frequency and exponential information from Laplace transform just by one look. Okay, so thanks for watching. See you guys again. Bye bye.